Good morning, everyone. My title is Direct Convolution and General Convolution. My name is Daeyeoul Kim. I came from South Korea. My university is Jeonbuk National University. In this talk, I will give 5 chapters. First, introduction and arithmetic functions and generalizations of direct convolution. First section, I'll give my result. So finally, I will state reference. First of all, I would like to thank Professor Dr. Mustafa Kuhan Yalchin for inviting me to this conference. One more, I'm also grateful to Professor Ilmaz Simsek for introducing me to this conference. And also I send my regrets to Professor Abdulnuz Bayat, who always treats me kindly, and Professor Vladimir Milovanovich, whom I always respect. I give a basic reference. The following 3 references have been prepared for this talk. First, Paul McCarthy, Introduction to Arithmetic Functions, Springer Block. Second is with Professor Bayat, I wrote polygon numbers associated to the sum of odd divisor functions. Finally, iterative stable numbers and iterative amicable pairs, also with Professor Bayat. Okay, I will give 3 references. In this talk, I'll give 3 notations. First is n, denotes the set of positive integers. The z is the ring of rational integers. Maybe c denotes the field of complex numbers. So first, I will give you some definitions. An arithmetic function is a complex valued function defined on the set of positive integers. So you see is more easy from N to C. For example, first example, maybe you know, is first Euler phi function is defined by this phi n is from 1 to n, then and GCD A and n equal to 1 is all number, cardinal numbers, then Euler phi functions. Second is, is the divisor function, divisor sigma kn, like this. D divide n, all sums is d to k. Third is useful is zeta function. This is not usual zeta function. Zeta kn is only to n to k. So zeta equal to zeta 0. So we know it's like this is n0, right? Is this. In this slide, I'll give some notations, and especially I'll give some operations of arithmetic functions. First is f and g are arithmetic functions. Their sums f plus g. We define is f plus gn equal to fn plus g. It's very useful definition. Second, and product is fg. You know this fgn is then equal to fngn. It's very useful, easy notation. Third is the direct convolution f star g is defined by f star gn sum d to the n fd times g n over d. Okay, for example, so zeta q, remember is n to the k. So this zeta to k, zeta star zeta n means is like this. D divide n, so all sums, then is zeta k d times zeta n over d. So zeta meaning is like 1, you remember, please remember this. This zeta is 1. Zeta k is, is original definition d to k. So this is usual definition, you know very well. So sigma kn. It's very special case. In this slide, I'll give some structures of arithmetic functions that are the set of arithmetic functions. Then I'll give some nice proposition. First is f and g and h are in R. That means it's f and g and h are arithmetic functions. Then it's very nice and useful is we have a commutative f star g equal to g star f. Second is they have is associative, so f star g and times h equal to f star and g star h. So associative rule. Third is distributive rule is star and plus. So f star g plus h, f star g plus f star h. Star is a direct convolution. So please use this is this very easy. So arithmetic function delta is defined by delta n. Is if n equal to 1, then 1. If n doesn't equal to 1, then we put is 0. Then it's very easy. F star delta equal to delta star f equal to f. So or arithmetic function f. So delta is, we know this delta is identity function. So we can get this. We have two operations, plus and direct convolution. This R is a commutative ring with unity delta. It's very useful fact. So in this slide, I will state its inverse of arithmetic function. Red R is the set of arithmetic functions. This is a ring. So f and g B R in R. Then is arithmetic function g is meaning is inverse. Meaning is of f, inverse of f is if like this f star g equal to g star f equal to delta. Is very well this definition. So if it has an inverse, sometimes we have no inverse, but if f has an inverse, it has a unique inverse, which will be denoted by f inverse. Okay, so we write this f inverse, meaning it's inverse of f. So we give one definition. This is UA. This meaning is the set of units in A. So that is f being R, f star f inverse equal to f inverse star f equal to delta. We say f, this is unit. So if f is unit, if and only if f1 does not equal to 0. This condition is very useful for inverse divisor function. One more, if f1 does not equal to 0, that is f has a unit, so we can construct the inverse f minus 1 inductively. So f minus 1 equal to 1 over f1, and f minus 1 n then is minus 1 over f1, sum d divide n, fd, f inverse d of n. So remember, n is greater than or equal to 2. Please remember this is useful. So I'll introduce is very well known is multiplicative function. So f is an arithmetic function. Especially f is called a multiplicative function. So first is fn doesn't equal to 0 for n least one integer n. And if is fmn equal to fm times fn. So for all mn with GCD, mn equal to 1. That is m and n are relative prime. Okay, I'll state this very useful proposition. F is multiplicative function, then f inverse is also multiplicative function. F is multiplicative, then f inverse is also multiplicative. And one more, f and g are multiplicative function, then f star g. Then is Dirichlet convolution f and g is also multiplicative function. It's very useful. So f multiplicate, f and g multiplicate, then f inverse multiplicate, f star g multiplicative function. So usually first we define is Möbius function u. So as an inverse of zeta 0, you know this zeta 0 n is n0 equal to 1, where zeta kn equal to n to k. So f equal to g Dirichlet convolution zeta 0 is, we can say this is also inverse, is like this inverse star star. And so we can get is g equal to f Dirichlet convolution mu. Mu is a Möbius mu function. So we define fn equal to some d divide n gd, if and only gn equal to some d divide n fd times mu n over d. We say this relation is the Möbius inversion formula. The Möbius mu function is maybe classically we define is like is undergraduate student understand this part. For any positive integer n, we define mu n as the sum of primitive n's root of unity. So mu n is, we have three choices: 1, -1, 0. Especially n is a square prime vector, and has a square prime vector then 0 is a square free positive integer with an odd number prime vectors is -1, even number of prime vectors then is 1. Maybe you know very well. So finally we remember, so mu1 equal to 1. We note that mu is multiplicative function, and sum the divide and mu equal to, if n equal to 1, 1, and is greater than 1, then 0. It's very well known result. So I will state this one more is the station, or more is the definitions. Especially let K be a complex valued function on the set of all ordered pairs is n and d, where n is a positive integer and d is a divisor of n, like this d divide n. So we define is K is like is the set is ordered pair and d from to C is by is ND ordered pair ND to K and D. K is one function on complex valued function. So we define is f and g is a K convolution of K. So first f and g be arithmetic functions. K conversions star K of f and g is defined by like this: f star g and OK is fd g d n over d is the same, but it's one multiplied at one factor. It's a k and d. So all numbers d divide n. F star g n equal to d divide n k m d f d g n over d. So for example, if our given k is a constant function whose value is 1, like this part is only 1, then this number is deleted. So we know this is the Dirichlet convolution. It's very easy. So K convolution is a generalization of Dirichlet convolution. It's okay. So if a given K satisfies the following, then A plus and K convolution is a commutative ring with unit delta. Its delta is, you know very well, its identity. First is first condition, delta unity in EU. So two operation is plus and K conversion. As if and only if, it's very easy. Is K and 1 is equal to K and N. So especially all number is 1. K and 1, K and N equal to 1, then is we have if and only if delta is unit. Second is K convolution is associative law. If and only if is K and D times KD equal to is K and E times K and over E and D over E. Third is commutative. If and only if is very easy. Same and N, K and D, and K N over D is very easy, useful. Then, since the Dirichlet convolution of multiplicative function is also multiplicative, so we want to start K. K convolution has such property. Is so K convolution of multiplicative functions is multiplicative if and only if this K M and D is K M and D times K and E. Then we can use this for condition. It's very useful. So A plus K convolution is commutative ring with unit delta. Okay, so generalizations of Dirichlet convolution, and especially it's a regular arithmetic convolution. So K convolution is called, especially a regular arithmetic convolution, meaning is called, then if the following condition are satisfied. So first is from 1 to 4 holds for K. So remember this. Like this 1, 2, 3, 1, 2, 3, 4. This. Okay. Second is only K and D is all and D, all the pair and D is only 2 is 0 or 1. C is mu K equal to zeta 0's inverse of zeta 0. Then mu K P alpha in -1 or 0. All 4 primes and then 4 alpha. Okay. So first I'll give you some example. Is the unitary convolution. So please remember, so some divisor D divisor n, a divisor of n is said to be a unitary divisor. For example, if this GCD D and n over D equal to 1, then we say a unitary divisor. For example, like this 6 is like this. To divide the 6, please remember 2 6 is 2 or 3. You know this is GCD 1. So we say 2 is a unitary divisor of 6. It's easy. So especially we say D is the divide N. We write. The final function mu is given by U and D. It's GCD D and N over D. Equal to 1, then we define 1. Otherwise cases we define 0. So we say this is unitary conversion. We say this is U conversion. Is regular, and is set to unitary conversion F star UGN. Then we define. So please remember D divide N, F D times Gn over D. This meaning is D N over D equal to 1 meanings. So especially this is a more generalized Möbius function. This if N equal to 1 in 1, otherwise case this is minus 1 to omega N. Omega N meaning is distinct prime divisor. The number of prime distinct prime divisor. For example, P1, PR, E1, ER. We say omega N is R. Remember? So listen to my result is, so I will explain. This result is with Professor Bayard. So I wrote this. Let us define the extended Möbius function and restrict the divisor functions for our in the sequel. Mu Tn is, we say this 0 and zeta T omega N. So 0, then if it's P to D divide N for some prime P. Otherwise case is zeta T large omega N. Large omega meaning is here like this, and equal to P1, E1, PR, ER is omega N is E1 plus ER. Maybe you know very well. So we define this. Then one more is we can define this DL and DJ. We define is D divide N, D2L as mu T J dt. So remember like this. So this. So here is zeta T equal to e to the 2 phi over T is a fixed primitive T's root of unity, and omega N denoting the number of prime powers of divisor N. Especially is in fact K and D is we can this is mu J sub T or D. So alternatively, so for L and M and N and S, T, J are integers with M and T is greater than 1, and S and J is greater than or equal to 0. Let us define the extended Möbius divisor function. So we can like this DL and DJ is please remember is at least Fi 1 factor greater than equal to T divisor like this factor. Then we can is times 0. So this part is we delete. So we T-free numbers, like T-free numbers, we can get only 2. We consider T-free numbers. So we say this is, we consider this, all these part numbers. Remember this here, zeta T is e to 2 phi over T. So this is fixed primitive this root of unity. Okay. So we want is iterated extended Möbius divisor function. So iterated is with the L, Tm to L and Tj. We say so this number is a iterated number is an integer. Then we can is one more iterate. But otherwise, then we can say we can put is 0. So like this. Is first is one more is function we can get this is we can get this like this. So D and D and D. So we can get like this we can iterate the functions. Okay, so we simply write. So this is especially is 1. We deleted this part is D and Tj. And one more is this third part is 0. Then we deleted this part is Dm and T. Okay, it's especially to that is 1. Then we do not use this D and T. Okay, or we write this. So special case is T equal to T2 is a very special case. So we write is Dmn, that is Dmn2 and the Dn and the Dn2. Okay, so Dn is a special case, Dn2 case. It's easily check that. So limit to T to infinite. Then T to L and T is a sigma Ln. Very useful. Okay, so finally I will write my result. So the order pair is M and N is an amicable pair, right? Is Sm equal to N, Sn equal to M with is M doesn't equal to N. This is we say amicable pair like this. It's from S we can get is prime to N. We can use this S, then we can N is M. So we have a cycle, then with this number M and N are amicable pair with S. Like this is we can use D and we can use D. Then some cases we can find these two number like this M and N. This is we say M and N. We say this amicable pair. Okay. And it's a collection of N1, N2, Nr is called sociable, meaning is N1 using S, then we find S2, N2, and another one more is N3. So we can use this Nr, then we find the S like this number. We say this number N1, N2, Nr is sociable. Okay. Please see this figure. Easy, useful. Okay. So we define with iterated amicable pairs of D. So Dmt equal to N, then Dn2 equal to M. Especially with M dip does not equal to N. Almost is iterated sociable is also same using Dn1t, Dn2, Dn2 is N3, so Dnr is N1. We say N1, N2, Nr is called iterated sociable of D. Okay. So especially in particular, some case N1 equal to N2 equal to Nr is the same. Then we say N is the iterated stable number of D. Okay. So, but it's very easy. One is a trivial number. So we define one is not an iterative stable number of D. It's very easy. D1 is 1, D2, 1 is D1, 1. So 1 is very trivial number. So we say 1 is not an iterative stable number. It's very, please, you see, this number is, we have a stable number. This number is amicable pair. This number, we say this is associable numbers. Okay, it's very easy. It's very easy notation. So please remember, stable, so amicable pair is associable numbers. So using this, so using T, so using Mathematica, so from n to 20, is very small number. So we can find this iterative stable number and the iterative amicable pairs. For example, is T equal to I is 2. We find that 12 is a stable number. So its amicable pair is 3 and 4. So T equal to 3 is 56, A714160, 7 and 8 amicable pair. So for example, 5992, 31 and 32 is more easy, but it's very considered is first. Please remember, it's 3 and 4 with times. 3 times 4 is 12. So third is 7 and 8 times is, you know, this is 56. And some more, 31 times 32 is 992. So very 3, 7, 31. Do you remember these numbers? Yeah, right. This number is Mersenne prime. So we can use very interesting problem. So 1 to 7 is Mersenne prime. So we have several questions. So first question is like this. Does there exist at least one iterative stable number n of d, t, for any t? So please remember. So this 2, 3, 4, 12. So we cannot find the 12, but this we only check is n to 20. So number is infinity. So we cannot know this number. So first question. Does there exist at least one iterative stable number of n of dt for any t? Is like this. Okay. Second question is question is very difficult. Then is a small question. Like if not, does not there exist at least one iterative stable number n of dt for a given special condition? For a given special condition, when we give a special condition, you find t. So, okay. So we can use one more, we consider this existence problem stable number. So please see, it's 2, 3, 11. It's okay, exist, but 12 we cannot find. Nearly all numbers is there exists is stable numbers, so we don't know. Okay, so I'll give some small is problem. Iterative stable numbers. So let MP equal to 2 to p minus 1 MP. MP is you know, is even perfect number. MP is a Mersenne prime, like this. You know this Mersenne prime is, you know, is MP is an even perfect number. Then 2MP is an iterative stable number of TP. especially TP is Madison prime case, then we can find this iterated stable number. Okay, let MP equal to 2 to P minus 1 be a Madison prime. Is by definition of 2D to MP. So D to MP is we have 2P, 2P minus 1. So 1 plus 2 plus 2P minus 1. So it's originally the divisor is 1, 2 square, 2P minus 1, 2P. But this P case then is we delete, or is the definition. So P is MP is Madison prime, so 1 plus MP. So this meaning is 2P minus 1. So we can get 2P minus 1 times 2P, so 2MP. Okay, so this is a stable number. Remember, stable number definition is like this. 2MP is 2MP. So this completes the proof of theorem. It's good. Okay, so this is P is very special condition. Okay, so time is very short, so I will finish this my talk. Thank you again, some professors, especially is Bayard and Professor Simsek, Archin, and Miller on SF. Thank you very much. I wish your conference have a good success. Finally, I will show reference. Okay, thank you for your attention. I will finish my talk. Thank you very much.